We're not just finding oxidation numbers for the fun of it, although I think it's pretty fun. We're doing it in order to find which thing in our reaction is oxidized and which thing in our reaction is reduced. We're going to find the oxidation numbers of every single element in every single compound in the reaction. For example, with H2 plus F2 making 2HF, we identify the oxidation number of hydrogen as 0 because it's a neutral element, the way we find it in nature. The same is true of the fluorine. It's a neutral element the way we find it in nature, so its oxidation number is 0. And the HF compound, however, is going to follow the oxidation number rules from our list. Fluorine gets its typical -1, since it's highest on our list, and there's only one of them. Don't worry about the coefficient in the equation. We're just looking at each HF molecule individually. For each HF molecule, we've got one fluorine with a -1 and one hydrogen, which ends up being a +1. We can see a change happening in the oxidation numbers of our elements in this reaction. The hydrogen starts out at 0 and becomes a +1 on the right side of the arrow. The fluorine starts out at 0 and becomes a -1 on the right side of the arrow. We look to see whether the number is going up or down. If the number goes up, that means the oxidation number is increasing. That would be an oxidation process for that element. Since hydrogen is going up from 0 to +1, we would say that hydrogen is oxidized in this reaction. For fluorine, its oxidation number is becoming more negative. It's going down, it's decreasing. That more negative oxidation number means fluorine is being reduced in this reaction. We're going to look at a bunch of different types of reactions in the context of redox reactions. These types of reactions are not always going to be redox, but they could be, depending on if things are oxidized or reduced as part of the reaction. Some of our redox reactions could also be single displacement, in other words, single replacement reactions. With our single displacement or single replacement reactions, one element is going to replace another one. In this example, the zinc is replacing the copper to be bound to the chlorine, and the copper is replacing the zinc as being the thing that's by itself. We can assign the oxidation numbers in this reaction. The zinc solid is in its elemental form, so it has an oxidation number of 0. In our copper 2 chloride compound, first of all, it's ionic. Anytime that we have an ionic compound, it's made up of ions, and the oxidation number of those ions is the charge on the ions. The chlorine has a -1 because it's in group 7A, and also because of our oxidation number rules. There are 2 of them, so that's a total of -2 coming from the chlorines. On the left side, we know our total charge has to equal 0, so the copper must be a +2. Then we get to zinc 2 chloride, and again, the chlorine is a -1, both based on our oxidation rules and the fact that it's in group 7A. It's a -1, and there are 2 of them, so that's -2 total from the chlorines. That means the zinc must be a +2. Then we get to the copper that's by itself in its elemental form, so its oxidation number is 0. We look at what's happening to each of the elements. The zinc is going from 0 to +2. The copper is going from +2 to 0. The chlorine is not changing. It's staying at a -1 oxidation number. Since the zinc is going from 0 to +2, we would say the zinc is being oxidized. And since the copper is going from +2 to 0, it's going down in oxidation number. So we would say it's being reduced. Which of the following is the reducing agent, and what is reduced in the following reaction? Zinc solid plus copper 2 sulfide solid makes the zinc sulfide aqueous plus copper solid. Is the correct answer A, zinc is the reducing agent and copper 2 sulfide is reduced. B, zinc is the reducing agent and sulfur is reduced. C, copper 2 sulfide is the reducing agent and zinc is reduced. Or D, sulfur is the reducing agent and copper is reduced. The correct answer is A. Zinc is the reducing agent and copper 2 sulfide is reduced. The thing that's reduced, the thing that's oxidized, the thing that's the oxidizing agent, and the thing that's the reducing agent are always going to be on the left side of the reaction. Zinc sulfide and copper solid in this reaction cannot be correct answers. We're looking at our reactants and seeing which is the reducing agent and which is reduced. Remember, the reducing agent is going to be the thing that's oxidized. In this reaction, the zinc is going from 0 oxidation number in its elemental form to having a +2 oxidation number when it's bonded with the sulfur. Remember, it's an ionic compound, so the sulfur is a -2 because it's in group 6A, and the zinc is a +2 to balance it out. The zinc is going from 0 to +2. That number is increasing, so you'd say that the zinc is being oxidized, and therefore it's going to end up being the reducing agent. The copper, on the other hand, is getting reduced. It's going from +2 when it's bound to the sulfur down to 0 when it's by itself. +2 down to 0 is a reduction. It's going down, so the copper is being reduced. Technically, the sulfur is not being reduced or oxidized. It's staying at a -2 oxidation number. However, when we talk about compounds that we're putting into our beaker, we would say that the copper 2 sulfide is our reactant that gets reduced, even though it's really just the copper part of it that's being reduced. Another type of reaction that could be redox is a combination reaction. Combination reactions have 2 or more things on the left side of the arrow, that is reactants, coming together to make just one single product. We can identify a combination reaction by the fact that there's only one product on the right-hand side. If something is changing in oxidation number, then it's going to be a redox reaction as well. In this case, we have nitrogen in its elemental form having an oxidation number of 0, hydrogen in its elemental form having an oxidation number of 0, and then in ammonia those elements have some different numbers. We assign the hydrogen first because it is on the list, but nitrogen is not. Hydrogen has a +1 for its typical oxidation number. Again, ignore the coefficient when assigning oxidation numbers. We've got 3 hydrogens each with a +1, so that's a +3 total from the hydrogens. We're adding up to 0 because ammonia is a neutral compound, so the total contribution to charge from nitrogen must be a -3. There is only one nitrogen, so it gets the full -3 oxidation number. Hydrogen is going from 0 to +1. That number is increasing, so hydrogen is being oxidized. Nitrogen is going from 0 to -3. It's going down, so you'd say that nitrogen is being reduced in this reaction. Another type of reaction is decomposition. Again, it could also be redox if something is changing in oxidation number. In this example, we have sodium hydride decomposing to make sodium and hydrogen. Decomposition involves one reactant on the left side breaking apart into multiple products on the right. We can identify our decomposition reactions by the fact that they have one thing on the left side of the arrow. We can figure out the oxidation numbers using our oxidation number rules. Sodium, again, is highest priority in the list since it's in group 1A. It gets its +1. There's one sodium, so that makes a total contribution to charge of +1. The hydrogen must be a -1, since the compound is neutral. On the right side of our arrow, we have elemental sodium, which is 0, and elemental hydrogen, which is 0. The sodium is going from +1 down to 0, so it is being reduced. And hydrogen is going from -1 up to 0, so it's being oxidized. Another type of reaction is a really special type of reaction in which one type of element undergoes both oxidation and reduction. This type of reaction is called disproportionation. A very common example is the disproportionation of hydrogen peroxide. In hydrogen peroxide, the oxygen ends up changing oxidation number, but in one of the products the oxidation number has gone up, and in the other product the oxidation number has gone down for the oxygen. Let's work out those oxidation numbers. In hydrogen peroxide, hydrogen has highest priority, so it gets its +1. There are 2 of them, so that's a +2 total on our left side, which means our right side must be a -2 total. We've got a total of -2 from the oxygens, but there are 2 oxygens contributing to that -2 charge. That means each individual oxygen must be a -1. -2 total contribution to charge divided by the subscript of 2 gives us -1 for the oxidation number of an individual oxygen in hydrogen peroxide. In the water molecule on the right, we've got hydrogen, which is a +1. There are 2 of them, so that's +2 total on the left, which means we must have a -2 total on the right. This time there's only 1 oxygen to divide that evenly into, so that oxygen gets its full -2 charge. Then we have the oxygen molecule, O2, which is in its elemental form, so it has an oxidation number of 0. The hydrogen is a +1 on both sides of the arrow, so the hydrogen is not being oxidized or reduced. The oxygen is actually doing both. When it becomes the water molecule, it's going from -1 to -2, so it's becoming more negative, which means it's being reduced. When it becomes the oxygen molecule, it goes from -1 to 0, so it's becoming more positive, which means it's being oxidized. Both are happening at the same time. You can sort of think of it as one of the oxygens being oxidized and the other being reduced. Our last type of reaction is combustion. We've talked about combustion reactions before. They have a hydrocarbon reacting with oxygens to make CO2 and water. We can identify our oxidation numbers in this reaction. The hydrogen in methane is a +1. There are 4 of them, so that's a total of +4 coming from the hydrogens. The carbon must be a -4 to make it a neutral molecule. Then we have oxygen in its elemental form, which is going to have an oxidation number of 0. On our right-hand side, we have CO2. Oxygen gets its typical -2, and there are 2 of them, so that's a total of -4, which means the carbon must be a +4 to balance it out. Lastly, we have the water molecule, which we've done before. Hydrogen is +1, there are 2 of them, so that makes +2 on the right side. That means oxygen is a -2. We compare the left side to the right side and see what's changing. The carbon is becoming more positive. It's going from -4 to +4. So we would say the carbon is oxidized. The oxygen, on the other hand, is going from 0 to -2. So it is being reduced. It's going down. It's becoming more negative in its oxidation number.